So in the previous lecture, we have started discussing common emitter amplifier, and this was the schematic, as you may remember. And depending on R5, if it is 0, this is common emitter. If it is not equal to 0, this is common emitter with degeneration, we said. The first thing that we should do is DC analysis. And for DC analysis, the transistor should be in forward active region. And for that purpose, what you should do is, first of all, you have to find the DC equivalent circuit by killing the AC source and by opening the isolation and bypass capacitors. Then the next thing is you assume that the transistor is in forward active region, set VB is equal to VB on, set IC is equal to beta FI base, and check the collector emitter voltage. If it is larger than saturation voltage, then it's okay, and you can continue with the small signal modeling. The small signal model of the bipolar transistor is quite similar to MOSFET, except you have this finite R-pi. This finite R-pi is different than the MOSFET case. And the T model is quite similar. This small RE is like 1 over GM in the MOSFET case. And in terms of value also, like 1 over GM is comparable to RE. And we find R-pi, R0, and RE by using the definitions in the previous lecture. But if you have any difficulty with these definitions, I told you that you can use this quick approach. GM is conductance I divided by V. GM is appearing at the collector, so use collector current. For voltage, for GM, R-pi, and RE, you always use VT, which is like 26 millivolt at room temperature. R-pi is appearing at the base, so you use I base current. RE is appearing at the emitter, you use I emitter current. Only for R0, instead of VT, you use VA because you want high resistance and VA is a high voltage. R0 is appearing at the collector, so you use collector current. Now let's analyze common emitter amplifier in small signal. For small signal again, you follow the same path. First, kill DC sources, which means that voltage sources are short, current sources are open. Second, short bypass and isolation capacitors. And third, replace the transistor with small signal model. And we did in here, so as you see between base, collector, and emitter, we replace the transistor model. We get rid of C1, C2, C3, and all the DCs are killed as well. And we end up with this circuit. Now let's find the three important parameters that we are seeking for. We are seeking for input resistance, output resistance, and the voltage gain. And for this particular case, let's assume that R5 is 0, so there is no degeneration. So for this case, we take R5 as 0, which means that there is no degeneration. Okay, and I am seeking for AV, Rin, and Rout. Let's define Rin and Rout. While finding Rin, you should exclude Rs. Rs should not appear in Rin expression. Rin is the resistance seen from here. And for Rout, again, you exclude RL. RL is load determined by the customer or end user. You shouldn't take it into account for Rout calculation. Rout is given from here. And I check R0. When I take a look at R0, one end is grounded. So it's not problematic for mathematical calculation, so I don't need to ignore it at any time. Rin is quite simple. The resistance seen from here has three components, R-pi, R1, and R2. these three resistances in parallel. So you can directly write Rin as R1 in parallel with R2 in parallel with R pi. Now try to analyze these results and try to compare them with the common source case. For the common source case, this R pi was infinite, but now it is not. And think about the typical values. It's like Vt divided by I base. It's like 26 millivolts divided by, let's say, I'm providing just some typical numbers. And of course, these numbers may change. Let's say 10 micron, sorry. Let's say it's like 10 micron, 10 microamps. So the result will be like 2.6 kilo ohms, which means that even if you use giga ohm resistors in here, even if you choose R1 and R2 as like 1 giga ohm, this R pi is limiting your input resistance. This tells me that in terms of input resistance, bipolar transistors are somehow worse than MOSFET transistors because you see some low resistance from the input. So please keep in mind that these are just like typical values and you can play with them. If this current is larger, you are going to end up with lower resistance, lower R pi, which is even more problematic. For R out, again, I think it's quite easy. For finding R out, what you should do is kill AC sources, independent sources, I mean. Kill independent sources. So this is shorted, which means that no current passing through here or here. So this voltage is 0. Therefore, no current passing through here. It's like an open circuit. So the resistance you see from here will be R3 in parallel with R0. So I can write it as R3 in parallel with R0. You can check it by applying, normal algorithm, like apply Vx, try to pass Ix, kill all the independent sources, and you will find the same result. If you have any question about this R out value, please do it by yourself and verify that it's like this. And if you compare this R out value with the common source case, they are comparable, they are the same, right? In that case, we find it like Rd in parallel with R0, which is exactly the same. And R0 values of these two transistors are comparable also. There's not a big problem over there. Let's find the gain of it. So let's first find V out value in terms of V pi. So V out is equal to minus Gm V pi R0 R3 in parallel with RL. Why? Because current is going in this direction. I have three parallel resistors and I can write V out with this negative sign with this term. Okay, now I need to find V pi. I think it's quite straightforward then. V pi is the voltage across this resistance. This node is grounded. In fact, you can separate them. You can, separate them from each other. So the left and right circuits are independent from each other somehow. So V pi is in fact just a resistor voltage division over there, which is R pi parallel R1 R2 divided by Rs plus R pi parallel R1 R2. In other words, Rin divided by Rin plus Rs. So if you put this term in here, the final result will be minus Rin divided by Rin plus Rs times Gm times R0, R3, RL. So this is the overall gain of a common emitter amplifier. So let's discuss on this result. First of all, we have a negative sign. So this is an inverting amplifier, like common source one. So let's write it somewhere in here. So we have an inverting amplifier, exactly like the common source one. This part, you want to make it close to 1. For MOSFET case, it was much more easier because you won't have RPi term in Rin. You can choose R1 and R2 as gigaohm, and you can have Rin very large. But now, first you cannot choose R1 and R2 as gigaohm. Why? Let's go back to the DC schematic. Somewhere in here. Yeah, in the DC schematic, these two resistances, R1 and R2, cannot be selected as very high. Why? Because they are appearing in the Thevenin equivalent circuit. As you increase R1 and R2 value, the potential drop across this resistor will be more, and you can transfer only some part of VDD voltage to bias the transistor. So it's a big trouble. You cannot choose giga-ohm resistances. You have to choose lower resistances at the input. The second thing is, even if you choose very high resistance values, still Rin is limited by RPi, and typical values are in the range of kilo ohms. So your Rin is unfortunately not very high. Because of that, you may not achieve very close to 1 values in here unless your RS value is low enough. So it looks like that because of this part, you are sacrificing some gain. This part is exactly the same with the MOSFET case, so they're almost the same. Expression is in fact almost the same, but this Rin divided by Rin plus RS may be a bit smaller than the MOSFET case. Let's compare the GMs. So for GM, let me open a new page. GM BJT is given as IC divided by VT. GM MOSFET is given by 2Kn ID in square root. Let's assume that we have the same bias. ID is equal to 1 milliamp. IC is equal to 1 milliamp. We are using the same bias. So this thing will be 1 divided by approximately 25 millivolts, which is like 40 milliamp per volt GM. For the same biasing, for a typical Kn value, let's choose it as 10 microamps per volt square. Let's choose a number where we can take the square root. Let's make it 20. So this thing will be 40 times 10 to the power minus 6 times 10 to the power minus 9 in square root. So the result will be 2 times 10 to the power minus 7 ampere per volt. You see the difference? There's a huge difference for the same bias for some typical Kn values. As you can see, most of the time for the same biasing value, GM BJT is larger than GM MOSFET. I hope I didn't make a mistake in the calculations. Oh, I did a mistake, sorry. I have to correct this. This should be like minus 3. If it is minus 3, this should be 4, minus 4. And it's like 0.2 milliamp per volt. Right? Okay, still, but the result is the same. So I can say that generally bipolar transistors have larger GM values compared to MOSFET. So when you go back to this expression, yeah, we sacrifice from Rin divided by Rin plus Rs, but on the other hand, GM is increased. So for typical biasing values, for similar biasing values, AV of common emitter can be larger than AV of common source amplifier. But input resistance is lower definitely. So as the outcome, I can say that AV of common emitter can be larger than AV of common source. Of course, it depends on the chosen values and circuit parameters. And Rin of CE is definitely smaller than Rin of CS. So we find all the three parameters which are important: Rout, Rin, and AV. And the results are quite similar to common source with some differences. What's going to happen if R5 is not equal to 0? Now let's consider that case. So if R5 is not equal to 0, this means that I have common emitter amplifier with degeneration. Again, we are looking for three important parameters: Rin, Rout, and AV. This is Rout. I exclude RL, of course. This is Rin, the resistance seen from here, and the voltage gain. And please do not forget to put terminal names for the transistor. For finding Rin, I can write Rin as R1 in parallel with R2 in parallel with R base, which I need to find, which is not known in this case. And what you should do is, if you cannot see it directly, which is the case now because it's not equal to R pi, this R5 makes everything complicated. What I need to do is go with the algorithm, which is like apply some Vx potential in here, apply some Vx potential in here, find Ix passing through it when all the independent sources are killed. So my equivalent circuit will be this one. R5, R pi, V pi. So this node is at Vx, this is Ix. I have GM V pi, R0, R3, RL. This is the circuit for finding R base, where R base is equal to Vx divided by Ix. In this schematic, this R0 is making things complicated. And remember that for AV and Rin calculation, if R0 creates mathematical complexity, you can ignore it. So I'm going to ignore it. I'm not going to put R0 in here because I am dealing with the input resistance. Okay. So if you solve Vx in here, Vx will be equal to V pi, which is R pi Ix, plus Ix plus Gm V pi times R5. Ix plus Gm V pi passing through R5. So this is the potential in here. So for finding Vx, I am writing this potential first, which is R pi Ix. Then I am writing this potential, which is R5 times Ix plus Gm V pi. So if you put V pi in here, eventually what you will find will be R base is equal to R pi plus 1 plus Gm R pi R5. Please look at here. That is IC divided by VT times VT divided by I base, which is like beta. So you can simplify it as R base. You can write R base as R pi plus 1 plus beta R5. So now iodine is known. We find iodine. I'm going to show you something different in here. For the hybrid pi model for BJT, we use this base emitter collector R pi GMV pi R0. And I know that this thing is in forward active. I know that I base times beta is, let's correct this, collector and emitter, IC. And this thing is valid for AC as well. Beta I base is equal to IC. So you can represent the same hybrid pi model as this. It's not going to change anything. If you have I base current, you will have beta times I base current passing through here. And this R0 then models the early effect. The additional current passing through here changes the overall collector current, so it's going to introduce this change, okay, on IC versus VC. So this increase in here is because of this R0 current, and the constant part is beta Fi, beta times I base, or beta Fi base. Okay, so you can use this model as well. You can replace GMV pi by beta I base. It's not going to change anything, and in some cases it helps a lot. Like what? Like when we were finding the input resistance, for example. Let's remember our previous circuit. We are looking from here. We see R pi. We see R5 in here. We get rid of R0 because we are looking for the input resistance. So we are trying to find R base. If I use this new model, I can see some things much more easier. So I have I base current passing through here. I have beta I base passing through here. There is the rest of the circuit, but it does not have any effect on the input resistance because this constant current source or controlled current source shows the effect. The rest is, yeah, it's important, but it's not important for finding R base. So with this knowledge, I can say that beta plus 1 I base current passing through this branch. What I can do is I can remodel this thing as R pi in here, beta plus 1 R5 in here, I base in here. So please look at it. The potential drop across this one, R5 beta plus 1 I base. The potential drop across this one, beta plus 1 R5 times I base. They are the same. So, what I do in here is this. I get rid of this current source by multiplying the resistance value by beta plus 1. What happened then? I don't need to worry about this current addition in here. I don't need to worry about beta plus 1 I base in here. Instead, I take this effect into account by increasing the resistance value by beta plus 1 R5. When you are looking from here, nothing changed. You still have I base current passing. You still have V pi plus this voltage. Look at the bottom one. When you are looking from here, the current is the same. The potential drop is the same. These two circuits are mathematically equivalent if you are looking from here. Okay, from the left-hand side view, they are equivalent circuit. And you can take this into account by multiplying R5 by beta plus 1 and put it in here. And this thing is known as reflection rule. And it helps you to find the input resistance in a much easier way. How? Let's take a look at the circuit. I am looking from here. The resistance is this thing plus in parallel with R base. For finding R base, what I have is R pi. I reflect the resistance at the emitter by multiplying by beta plus 1 added to R pi. So the resistance is R pi plus beta plus 1 R5. R pi plus beta plus 1 R5. So I end up with the same result. In the previous solution, I draw the small signal model. I do some calculations like this, write the expressions and so on and so forth. But if you ignore R0 and if you use the reflection rule, it is much more easier. So what you should do is, if you have any resistance at the emitter end, you can take it into account by multiplying it by beta plus 1 and add it next to R pi. So you then get rid of the effect of the right part. When you are looking from here, you see the same equivalent circuit. Mathematically, nothing changes as long as you are looking from here. The next thing we should do is finding the voltage gain. Let's find the voltage gain. For the voltage gain again, if R0 is creating problem for you, you can ignore it. So I'm going to ignore R0 in here. So let's write V out. V out is very straightforward, I guess. The current passing through here, multiplied by R3 in parallel with RL, which is minus Gm V pi R3 in parallel with RL. I need to write V pi. How we are going to write it? First of all, there is a voltage division between V signal and V base. Then by using the reflection, you can write another voltage division. So what I can write is VB is equal to Rin divided by Rin plus R signal times V signal. It is the first voltage division in here, total resistance Rin. The total resistance Rin. So it's going to be Rin divided by Rin plus Rs. That's correct notation. Now I need to write V pi in terms of VB. Remember the reflection. The circuit is something like this. if you use the reflection from the left side. R5, R pi, V pi, this is VB. So I can say that V pi is equal to R pi divided by R pi plus beta plus 1 R5 times VB. So if you add them up all together, the overall gain will be minus Rin divided by Rin plus Rs times Gm R3 in parallel with RL times R pi divided by R pi plus beta plus 1 R5. I'm going to go one step further. If you divide both parts in here by R pi, the result will be minus Rin divided by Rin plus Rs times Gm R3 in parallel with RL times 1 over 1 plus beta plus 1 over R pi. Remember that beta plus 1 over R pi is in fact equal to beta plus 1 divided by Vt over I base, which is 1 over Re, which is in fact Gm, almost Gm. So you can write it as Gm R5. So this will be the final expression. And please note that this expression is exactly the same with common source with degeneration case. We end up with the same expression. It was the same. The overall gain decreases by 1 plus Gm times the source resistance, or in this case the emitter resistance. The rest is the common emitter gain. Of course, there are some differences between common emitter with degeneration and common source with degeneration. Your Rin is lower because of R pi. Oh, sorry, your Rin is not as low as R pi anymore. I mean, if you take a look at the previous slide, your Rin is improved. So this Rin is better than common emitter case, but still less than common source case. And GM BJT is larger than GM MOSFET, but the overall gain is decreased by 1 plus GMR5. So to summarize, common emitter with degeneration Rin is better than common emitter case. Why? For Rin of CE bus, R pi in parallel with R1 in parallel with R2. Rin of CE with degeneration is R pi plus beta plus 1 R5 in parallel with R1 in parallel with R2. So improved due to reflection. AV is less than CE by 1 plus GMR5. We sacrifice from AV, but we improved the input resistance by using degeneration. Like in the common source case, because of degeneration, we have a more stable amplifier. I mean, if you choose GMR5 much larger than 1, then these GMs are gonna cancel out, and you will have a transistor independent gain like in the common source with degeneration. So keep in mind that this is for common emitter with degeneration. And the last term that we should find is output resistance. Let's find the output resistance. For the output resistance, the rule is kill independent sources, apply Vx, find Ix passing through Vx. Rout is Vx over Ix. So I'm going to apply Vx in here. I will find Ix passing through it when I kill the independent sources. And I'm going to make a trick in here because I know that Rout is equal to R3 in parallel with something called R collector, the resistance seen from here. And if I define a new current Ix prime, this R collector will be Vx over Ix prime, which is much more easier to calculate. This is going to simplify the mathematical analysis a lot. So I'm going to find R collector first, then I will find R out. So in that case, your Vx value will be the voltage drop across R0 times Ix prime minus Gm V pi plus, let's say that this is VE plus VE. For the sake of simplicity, I'm going to assume that Rs is equal to 0. Only for this solution, okay? Please do not assume it's 0 when you are solving by yourself. But I just want to show you some technique. By taking Rs into account right now, things are getting complicated. But just for the time being, assume that Rs is equal to 0. This is going to simplify my work significantly. Then, because of that, this node will be grounded and VB will be grounded. So VE will be equal to minus V pi. Okay, so this VE will be equal to minus V pi. So Vx can be written as R0 Ix prime minus Gm V pi minus V pi. But what is V pi? This current passing through here is Ix prime. And we have two resistors in parallel then. And this V pi will be then Ix prime R5 in parallel with R pi with a negative sign. So Vx will be equal to R0 times Ix prime plus Ix prime Gm R5 in parallel with R pi, R5 in parallel with R pi plus Ix prime R5 in parallel with R pi. Therefore, R collector will be R0 times 1 plus Gm R5 R pi plus R5 in parallel with R pi. And from here, R out is equal to R3 in parallel with the thing that we find. Well, the expressions are quite complicated and it may be boring sometimes, but we can, come up with some results. First of all, this thing is R0 times something larger than 1. So this term is definitely much larger than this term. So this part can be ignored. That's one thing. You can ignore it. The other thing is, this R collector is a huge value, R0 times something. Like if R0 is 100K, this is going to be definitely larger than 100K. But this R3 is a discrete component. It's in the range of a few kilo ohms. Most probably, this R3 is much smaller than our collector. So I can say that R out is approximately equal to R3. But of course, you have to make all these calculations. One important thing in here, when I am finding this Ix prime and finding the resistance seen from here, some of your friends can ask, why don't we use reflection? How come this current is going like this and this without using that beta or beta plus 1 thing? The answer is this. In the previous calculations, RIN calculation or AV calculation, I was looking from here and I was trying to take into account the effect of this controlled current source. When I use reflection, I get rid of this current source as I already take into account its effect. But now for R out, I am looking from here, and this current source is already appearing in the expressions, like this one. At this point, the circuit is like a regular 201 circuit. You cannot make any reflection. You cannot put the relation between here and here. You don't need to, because that effect is already included when you put this into account. When you're looking from here, you don't know whether, I base current is passing through, beta I base current is passing through. You don't know it. You have to solve it like a regular circuit. So in that case, this R pi and R5 appears like typical parallel resistors. That beta and beta relation or beta plus 1 relation is already included when you say V pi and GM V pi in here. That's the most tricky part in here. And by using this, since you know how to find it, if I don't have Rs is equal to 0 in here, you should be still solve it. It's going to be a bit more complicated because now finding V pi, you have to use resistive voltage division in here. It's going to make the thing complicated, but please solve it as an exercise to see whether you understand the solution or not. So as an exercise, solve R out when Rs is not equal to 0. You will find a similar result at the end, but please solve it and make sure that you understand it. We can have more discussion in here, like, the effect of R pi, and because of this R pi, like, it's the limiting factor, GM times R pi will be beta, so the collector current, R collector, the current that you can see from here can be at most 1 plus beta times R0. It cannot be larger than that, but that is out of scope of this course. Maybe in 414 we can discuss more in detail if you take it. But basically, this degeneration R5 improves the output resistance of the transistor. If you do not have this R5, you see R0 from here. But once you have R5 in here, the resistance seen is significantly improved and much larger. That's one of the advantages of common emitter amplifier with degeneration. So I think we can stop here for this lecture, and next week we will continue with common base and common collector amplifiers, and then we are going to combine them to make a more complicated amplifier structure, multi-stage amplifiers.